we're going to start discussing section 5.3, which is leading us into balancing chemical equations and eventually stoichiometry, which connects the balanced equations to what we just learned of molar masses. A chemical change occurs when something new has been completely transformed into something totally different. So there's two questions you should ask yourself when that happens. Question 1, is it the same thing? So if you can sit back and say, okay, this is the exact same thing, just a different version of it, then there was no chemical change. For instance, if you take water and you put it in the freezer and make ice, the molecules didn't change. It's still H2O. Nothing actually happened. It's just changed forms. Therefore, it's the same thing. There was no chemical change there. Whereas if you took a piece of paper and set it on fire, and you looked at the paper afterwards, the paper would now be ash. It's still not paper anymore. You can't put it back together and write on it again. Which leads us to the next point. Can you change it back? If the answer is yes, then it's not a chemical change, it's a physical change. If the answer is no, it's a chemical change. For instance, if we go back to that water example, we put water in the freezer to make ice. We can take it back out of the freezer and turn it back into liquid. That's not a chemical change because we can go back and forth very easily. Whereas with the paper, you can't form it back into paper again. Now if you notice here, observe by a number of different things. For a chemical change to occur, a physical change must occur as well. You will see something happen as a chemical change is happening. For instance, when you took a piece of paper and you burned it, that same example I've used twice now, it gives off heat. That giving off heat is an example, a physical example of the paper changing. Plus it changed colors. Plus it got smaller. There's physical things you can see that tells you that chemical changes occur. Now don't be fooled into thinking that every time you see a physical change, a chemical change is happening. Because there's a lot of times that you'll see bubbles, for instance. That means that's still a physical change. For instance, if you open up a can of pop, the bubbles come up and they evaporate into the air. That's carbonation. Well, you can actually put carbonation back into a pop and it's going to be exactly the same. So therefore there is no chemical change there because you can change it back. Those are the two questions you have to ask yourself when you do these. These are just some examples. These are not the only examples. For instance, it can change color. This is an example of changing color. This is after it rusts, which means oxidized. So it's nice and shiny and metallic looking, and then it becomes reddish and brittle. That's just one example. Formation of bubbles. For instance, if you mix vinegar and baking soda, you can produce a solid, or you can produce heat, like burning of the paper. So let's think about these a little bit. Burning a candle. When you're done burning it, can you put the candle back together again and reburn it? Can you unburn a candle? The answer is no. That means that is a chemical change, because you cannot unburn a candle. Ice melting. Can you unmelt an ice, which is another word for freezing? The answer is yes. So that is not a chemical change. Burning toast. Can you unburn toast? No. That means that's going to be chemical. And water turning to steam. Can it turn back into water? Yeah, it can condense. It can cool down. That means that's physical. So that means that is not one of the ones we want. So A and C. Alright, so if we look at how a chemical equation is written, we can see several different parts. We can start on the left-hand side. That's our starting point. Those are the reactants. That's where we're beginning. On the right-hand side, you'll see the products. That's the finish line. That's the end. This is being converted over here. Now notice you have carbon and oxygen on the left-hand side. You still have carbon and oxygen on the right. They didn't go away. They're just rearranged differently. The arrow divides the two, which is simply saying that the left side is becoming the right side. The reactants are becoming the products. This right here, that triangle, means heat. Heat is given off. So let's take a closer look. So, if you have multiple products or reactants, they're going to be divided by the plus sign. An arrow divides both the left side from the right, or the reactants from the products. Triangle means reactants are heated. S is for solid, L is for liquid, G is for gas, AQ is for aqueous. That's just simply saying the physical state. It's not telling you anything more than that. You don't have to count it in when you're balancing the equations. So once again, we have one carbon, two oxygens. On this side, on the right side, we have one carbon, and two oxygens. We didn't change it. All we did, notice that there's a plus sign here, but there's no plus sign here. That's because these are now all bonded together on this side, whereas these are not on the left side. The atoms, the quantity of atoms did not change. That's called the conservation of matter. The left side and the right side are the same because of the conservation of matter. Once you have a chemical equation written, and you have the subscripts, which are the little numbers, you cannot change those little numbers. Those little numbers are there because they're telling you the ratio of which the atoms are supposed to be. If you change these little numbers, you're changing what the compound is, and that you can't do that. You also can't insert numbers. Never, ever, ever insert numbers in there. The numbers that we're going to add are always going to be in front of that compound. You can't put it in the middle of the compound. So if we take a look here, state the number of atoms of each element on the reactant side and the product side for each of the balanced equations. So, we have phosphorus and bromine. We have 4 phosphorus. So for phosphorus, we have bromine. We have 4 phosphorus. Notice this 4 in front. That means we're multiplying this whole thing in this PBr3 all by 4. So that means we have 4 phosphorus. This 6 means we have 6 Br2s. So we have 6. We're going to have 2. For every Br2, we have 2 Brs. So 6 times 2 is 12. We have 12 bromines on the left. We have 4 of these sets. In each set, we have 3 bromines. So that means we have 12, because 4 times 3. The next one aluminum, iron, and oxygen. Aluminum, iron, and oxygen. Let's start with aluminum. We have 2. There's no subscript, so there's nothing to multiply it by. On this side, a little 2, that means we have 2 of them, no number in front, so it's times 1. Iron. We have a little 2, which means we have 2 irons, nothing in front. We have a 2 in front of the iron on the right-hand side, and no subscript, so it's 2 times 1. Oxygen, 3 times 1. Remember, there's an invisible 1 here. And on this side, we have 3 times 1 is 3. Alright, so let's try to balance this one ourselves. We have iron, oxygen, and hydrogen. So on the left-hand side, we have 3 irons. On the right-hand side, we have 1 iron. On the left-hand side, for oxygen, we have 4 oxygens. On the right-hand side, we have 1. Hydrogen, we have 2 on the left and 2 on the right. Alright, let's just start from the top. 3 and 1. Those are not balanced yet. We have 3 here, and we have 1 here. The only way to get these to be equal, the only number that's divisible by both 3 and 1 is 3. So if I multiply this side by 3, there's an invisible 1 here, so it's going to be 3 times 1 is 3. That makes that 3. Okay, now oxygens. We have 4 on the left, and we have 1 on the right. So the only way to get these equal to each other, the only number that's divisible by both 4 and 1, is 4. That doesn't change anything on the left, but on the right-hand side, 4 times 1 is 4. Now, in the process of doing that, we multiplied H2O as a whole by 4. That means we no longer have 2 hydrogens here. We now have 8. Which means we need to fix this over here. We multiply this by 4. 4 times 2. That becomes 8 as well. So our balanced equation is 1, 4, 3, and 4. 1, 4, 3, and 4. Alright, now if you have polyatomic ions in the mix, sometimes it's easier to keep them as a set than to try to divide them out. For instance, we have PO4 phosphate on the left-hand side. We also have it on the right-hand side. If we keep those as a set, like it says right here, it makes the multiplying out a lot easier. Otherwise, we'd have to say phosphorus and oxygen individually, and we'd have to say we have 2 phosphorus and 8 oxygens over here, and 2 phosphorus and 8 oxygens over here. That just, all it does is increase our workload. Notice it's still the same, 2 and 8, 2 and 8. It's just done as a set now. Okay, we're going to do a little bit more practice with some balancing of chemical equations. So let's take a look at these. We have 3 elements here. We have iron, we have oxygen, and we have carbon. We have 2 irons and 1 over here. And oxygens, we have 3 oxygens and 2 over here. And carbon, we have 1 carbon and 1 on the right. So to get the irons matched up, 2 on the right, 1 on the left, if we multiply this by 2, that becomes 2 because 2 times 1 is 2. Oxygens. The only number that's divisible by both 2 and 3 is 6. Therefore, we want to get both of these numbers to 6. So if I put a 2 in front of here, that becomes 2 times 3, which then becomes 6. And I could put a 3 here, and 3 times 2 is 6. Uh-oh, that messed up our irons in the process. Iron on the left is no longer equal to 2. We now have 2 times 2 irons. That makes that 4. That means we also need to fix the one on the right to make that 4. Now let's take a look at the carbons. We have 1 on the left. Now we actually have 3 times 1, we have 3 on the right. Well, this will be an easy fix though, because all we have to do is multiply C by 3. So our coefficients end up being 2, 3, 4, 3. So if we look at here, 2, 3, 4, 3, the answer is number 2. Alright, our next one. We have aluminum, iron, and oxygen. So aluminum on the left is 1. On the right, it's 2. Iron, we have 1 iron on the left. There's an invisible 1 here, and 1 iron on the right. And oxygen, we have 1 on the left. We have 3 on the right. 3 times, there's no number in front, so 3 times 1 is 3. So, starting from the top, we have aluminum, 2 on the right. I'm going to multiply aluminum by 2 on the left-hand side, so that way those equal out. Irons, we still have 1 and 1, so those are still okay, so let's move on to oxygens. Oxygen, we have 3 on the right. We have 1 on the left. If I multiply FeO by 3, that gives us 3 oxygens. However, that ends up changing our iron at that point. So instead of having 1 iron, we now have 3. That's an easy fix. We're just going to go back up to here and multiply that by 3. Where there's no line here, nothing on top of the line there, that means it's a 1. 2, 3, 3, 1. 2, 3, 3, 1. Our answer is the first one. The last example we're going to have contains a polyatomic ion. Notice SO4 is here. SO4 is here too. So I'm going to keep that as a set to make my life a little bit easier. So we have aluminum, hydrogen, and SO4 as a set. We have 1 aluminum on the left, and we have 2 on the right. Hydrogen, there's 2 on the left, and there's 2 on the right. And sulfates, as a set, we only have 1 of them here. Notice I had to put parentheses around SO4 because I don't want to mistakenly take that 4 and bring it down. There's actually, that as a set, we only have 1 set of that. Whereas we have 3 sets. Notice it's on the outside of the parentheses there. We actually have 3 sets of SO4. Alright, there's a couple different places that we could start. Let's just start from the top. Aluminum, 2 on the right, 1 on the left. I'm going to multiply aluminum by 2. Hydrogens are okay so far. Sulfates, we have 3 on the right. We only have 1 on the left, so I'm going to multiply H2SO4 by 3, giving us 3. However, that changed our hydrogens in the process. That now becomes 6. So if we look on the right-hand side, That changed our hydrogens on the right. We need to change the hydrogens on the right. If we multiply H2 by 3, 2 times 3 is 6. Now everything is balanced. So if we look, that's an invisible 1, 2, 3, 1, 3, 2, 3, 1, 3. Our answer is the second one. That's the end of section 5.3 in balancing chemical equations. If you need more help, there's more tutorials and practice in your folder.